Hello linear algebra students. Today's video lecture is a continuation on our discussion on vector spaces in Rn. Now the vectors of a set S, which is a subset of Rn, are linearly independent if no vector in the set can be expressed as a linear combination of the other vectors in the set. Otherwise, the vectors in the set are linearly dependent. Now determine whether each set of vectors in R2 form a linearly independent set. If dependent, establish a linear relationship between the vectors. Also graph each set of vectors. Let's focus on set 1. Let's label these vectors u and v. There are only two vectors in this set. Well, since there's only two vectors in this, we simply need to check whether any vector is a multiple of the other vector. Now in this particular case, we can see that if you multiply vector v by -3, you will get vector u. So vector u is equal to -3 times vector v. And similarly, I can say that vector v, therefore, is equal to -1/3 of vector u. Therefore, each vector is a linear combination of the other vector. And in this case, because there were only two vectors in the set, we can say more precisely that each vector is simply a multiple of the other vector. This means that the two vectors, u and v, are linearly dependent. I will use LD for linearly dependent and LI for linearly independent. Now let's graph the two vectors. I will place the origin there and then graph both vectors u and v. Now when graphed, you can see that the two vectors do terminate on the same line that passes through the origin. In other words, they are collinear along a line through the origin, which suggests that they are scalar multiples of each other. Let's look at the set 2. Again, there are only two vectors in the set, so we just have to determine if one is a multiple of the other. The second vector is the same, so let's call that vector v still, and the first vector is new, we'll call that vector w. And w is not equal to some scalar multiple of v, because to scale 1 to 3, you would have to triple 1, but if you triple -2, you don't produce the -1. Therefore, v is not some scalar multiple of w either. So these two vectors are linearly independent. Graphically, what this means, let's graph both of these vectors. And when you do so, you'll notice that the two vectors are not collinear. There is no line through the origin on which both of these vectors terminate. The vectors terminate along this line, but that's not a line through the origin. Okay, let's look at set 3. The second vector is still vector v. The first vector is new. We'll call that vector x. But because the x vector is the 0 vector, you can scale vector v to become it. So it is true that 0 times vector v will give us vector x. So this is a trivial linear combination of one vector to produce the other. Now it is not possible to express v as a multiple of x, but because we can express x as a scalar multiple of v, then we have the two vectors are linearly dependent. In general, if a set of vectors contains the 0 vector, then that set will automatically be a linearly dependent set of vectors. I won't bother graphing these vectors. Let's look at set 4. Set 4 has the same vectors w and v that we referred to before, and it has a new vector. We'll call that vector y. Now this time we have a total of 3 vectors, but in R2. Is it possible to express any one of these vectors as a linear combination of the other two? Now we can examine this by guessing and checking and seeing if it's possible to come up with a linear combination of two of the vectors that produce the third. For example, if we double the vector w and then remove the vector y, so double this entry and then remove that entry, so we get 6 minus 5 and we get this entry. Double this entry, remove this entry, and we get this entry. So this linear combination of w and y will produce the vector v. Thus, it is possible to express v as a linear combination of the other two vectors in the set. So right away, we can say that this set of vectors is linearly dependent, or you can also say not linearly independent. Once you have this equation, though, you can solve it for any of the vectors w or y. If I solve for vector y, I get vector y is equal to 2 times vector w minus vector v. And if I solve this for vector w, I get vector w is equal to 1/2 of vector y plus 1/2 of vector v. Therefore, we can express all of the vectors in the set as linear combinations of the other two. Now, graphically, what's happening? Here are the vectors w and v in the set, and now let's also graph vector y. Now none of these vectors are collinear, but they are all coplanar. In fact, the span of vectors v and w alone will cover all of R2. Thus, it's possible to obtain vector y by doing a linear combination of v and w. But also, v and y can be used as two vectors whose span is all of R2, suggesting that vector w can be obtained by doing a linear combination of v and y. And similarly, we could use vectors w and y to span all of R2, suggesting that vector v, which is in R2, can be expressed as a linear combination of w and y. So again, in summary, these three vectors are linearly dependent. Okay, let's go to the next page. Determine whether each set of vectors in R3 form a linearly independent set. If dependent, establish a linear relationship between the vectors. Also use technology to graph each set of vectors. Set 5. Now set 5 has only two vectors in it. They're both three-dimensional. But because there are only two vectors, we simply need to determine whether either vector is simply a multiple of the other. So to go from 1 to 4, we would multiply by 4, but that's not the same scale factor to convert 2 to 1, nor is it the same scale factor to convert -1 to 2. So these two vectors are not multiples of each other. Let's call them u and v. And u cannot be constructed from v by scaling it, nor can we scale u to construct v. So these two vectors are linearly independent. Let's turn to a graph. Here I'm using GeoGebra 3D, and I've graphed the vectors u and v, and you can see that they do not point along the same line in 3-space. Therefore, it's not possible to scale one of these vectors alone to obtain the other one. Okay, let's look at this set number 6. The first two vectors here are repeats, so they are u and v again. We have a new vector, we'll call that vector w. Now to determine whether any of these vectors is a linear combination of the other two, we simply have to guess and check until we can find a relationship between the vectors, whereby a linear combination of two of them will produce the third. Before too long, we would come up with the following relationship. I can construct vector w by doubling vector u and then removing vector v. Let's test this. Double 1 and then remove 4. So that's 2 minus 4, and sure enough, we get -2. Double 2 and remove 1 produces 3. Double -1, remove 2, produces -4. Once you discover one such relationship, you can basically just solve this equation for the other two variables. For example, vector v therefore must be 2 times vector u minus vector w. And vector u must be 1/2 of vector w plus 1/2 of vector v. Thus, the three vectors, u, v, and w, are linearly dependent, which means that any one vector is in the span of the other two. For example, vector w would be in the span of vectors u and v. Let's look at this graphically. Going back to GeoGebra 3D, I will add vector w to our imagery. And you'll notice that the span of vector u, which is red, and vector v, which is green, will produce a plane. And we'll also notice that the vector w, which is blue, is in that plane. Let me go ahead and reveal that plane. And then we can see that all three vectors are coplanar. When that happens, then any one vector can be found by doing a particular or certain linear combination of the other two vectors. Any one vector is in the span of the other two, the span being all vectors in this plane. And to produce this plane, you only need to span two of these three vectors. Any two of these three vectors. Now before we move over to set 7, I want to show you another way to think about this. Take any one of these equations and move all the variables to one side. For example, I'll copy this equation and I'll subtract vector w to the other side and then switch sides. It creates this vector equation, and notice we do have the 0 vector here. Don't just say 0 scalar, it has to be 0 vector. Both sides of this equation have to be three-dimensional vectors. But this suggests that because there was a linear relationship between all three vectors, we can move them all to one side, getting a 0 vector on the other side, and then recognize the following fact. If I take the vectors u, v, and w and make a matrix out of them, and then multiply that matrix by the coefficients of u, v, and w as a vector, then this produces the 0 vector. If we think of this as matrix A, then the system A times some vector equals the 0 vector. We have found a non-zero solution. Non-zero meaning that at least one of these components is not 0, not that none of them are. This is known as a non-trivial solution. The trivial solution to this equation would be if vector x itself was the 0 vector, because the 0 vector times the matrix A, of course, trivially gives you the 0 vector back. But when x has a non-zero component, and we still have a true statement here, then we call this x here a non-trivial or a non-zero solution. And if this system has a non-zero solution, that will mean that one of these components will be non-zero, which means that at least one of these coefficients will be non-zero, which means that I can ultimately solve this equation for u, v, and or w in terms of the other vectors, which would suggest that the vectors are linearly dependent. This is going to provide a way whereby we can determine if a set of vectors form a linearly independent or a linearly dependent set. We will make a matrix out of those vectors, multiply it by some unknown vector, set it equal to the 0 vector, and then solve for that unknown vector. And if the only solution is the 0 vector, that will suggest that the vectors that form the columns of A are linearly independent. But if we can find a non-trivial solution to this equation, then that will suggest that the columns of A form a set of vectors that are linearly dependent. Let's use this thinking on this next set, set 7. So I will form a matrix whose columns are these 3 vectors. And then we want to ask ourselves, can I find a non-trivial solution? Let's call this vector C1, C2, C3, such that when you multiply this matrix and this vector, that we get the 0 vector. I'll convert this to an augmented matrix first, and then I'm going to use technology to put this in reduced row echelon form, and we will get the following. Notice that there are no free variables. We have 3 pivots. Each pivot stands for the coefficient of C1, C2, and C3 respectively. So the first row would read that C1 has to be 0, C2 has to be 0, and C3 has to be 0. When 0 is the only solution, it suggests that the columns, which are the vectors in our set of this coefficient matrix, are linearly independent. So these were the vectors u, v, and a new vector, we'll call this one x. And we can conclude that the vector set u, v, and x, that these vectors are linearly independent. Okay, let's graph these in technology. Okay, here are the 3 vectors. The black vector is our vector x, and the green and the red are the vectors v and u respectively. But notice that because the vector x is not coplanar with the green and red vector, let's go ahead and reveal that plane again, that it's impossible to do a linear combination of the green and the red to produce the black, because every linear combination of green and red would be somewhere on this plane, and the black one is not on that plane. Similarly, if you were to imagine a plane that contains black and green, that plane would not contain red. And similarly, if you were to imagine a plane that contains black and red, that plane would not contain the green. So it is not possible to do a linear combination of 2 of these vectors to produce the third, which is why we say that they are linearly independent. Okay, let's go to the next page. Now let the vectors of a set S, which is a subset of Rn, form the columns of a matrix A, so similar to what we were just doing. Now the columns of A are linearly independent if and only if Ax equals 0, where x and 0 are vectors, has only the trivial solution x equals 0. This is what we just discussed, but now formally summarized. Furthermore, if Ax equals 0 has only the trivial solution, if you recall from our equivalence theorem, that suggests something about the matrix A, if A is square, that its determinant is non-zero. So if A is square, then the columns of A are linearly independent if and only if the determinant of A is non-zero. So we can use the determinant to determine whether the columns of A form a linearly independent set or not. Of course, this only works if the matrix A is square. Now in set 6 and 7, these are repeats. These are the same sets that we saw up here, 6 and 7. But because they are 3 vectors in R3, when you make a matrix out of them, that matrix will be square. We just simply have to calculate the determinant of that matrix to determine whether or not these sets are linearly independent or dependent. So on set 6 first, set up the determinant of the 3 by 3 matrix. So absolute value bars, then put the 3 by 3 matrix in there. And using technology to calculate the determinant, we get the determinant 0. If you get a determinant of 0, it suggests that the vectors are linearly dependent, which means that any one vector could be expressed as a linear combination of the other two. In set 7, if we do similarly, the determinant of this matrix will be 20, which is non-zero. If the determinant is non-zero, that means that the columns are linearly independent. So the vectors in this case are linearly independent, meaning no vector can be expressed as a linear combination of the other two. Now, the determinant does not help us find out what that linear dependent relationship is in the case where the vectors are linearly dependent, so that we would still need to either figure them out from inspection or set up a matrix equation and solve, as we did on that last example. Let's now look at set 8. 8 has 3 vectors in it, but they are vectors in R4. They are 4-dimensional vectors. So if I were to make a matrix out of these 3 vectors, it would be a 4 by 3, which is not square, so I cannot calculate its determinant. So if I want to determine if these 3 vectors are linearly independent or dependent, I would simply need to make a matrix out of them, a non-square matrix, multiply it by a vector of coefficients, and set that equal to the 0 vector, and determine whether or not we get only the trivial solution or whether we get a non-trivial solution. I'm going to go directly to an augmented matrix here. Here's the coefficient matrix, which is just the 3 vectors. Then we'll multiply that by some vector C1, C2, C3 to get the vector 0, 0, 0, 0, forming my augmented matrix. Now I'll use technology to put this in reduced row echelon form, and then examine where the pivots are. There's 3 pivots, 1 per column. These first 3 columns represent the coefficients of C1, C2, and C3. So this suggests that C1 has to be 0, C2 has to be 0, and C3 has to be 0. So this is only the trivial solution, and when that occurs, it means that the vectors that form the columns of the coefficient matrix must be linearly independent. Let's call these vectors on this page vectors u, v, and w, so I can refer to them. So these 3 vectors, u, v, and w, which form the columns of the coefficient matrix, are linearly independent because we had only the trivial solution. Set 9, you will notice that the first 2 vectors are the same, but I changed the third one. So we'll say u and v again for the first 2, and we'll call this last one vector x. Once again, we'll have a non-square coefficient matrix. This would be 4 by 3, so we can't calculate the determinant. So we simply create a matrix out of these 3 vectors, multiply that matrix by a vector C1, C2, C3, and set it equal to the 0 vector, and solve for C1, C2, and C3. So here is our augmented matrix, and then I will use technology to put this in a reduced row echelon form. Then examine the pivots. There are 2 pivots. The third column does not have a pivot position, therefore C3 is free. The first row would read that C1 minus C3 is equal to 0. Second row would read C2 plus C3 is equal to 0. And of course, C3 is free. So we're looking for just one solution. There will be infinitely many. So let C3 just be any one number, such as 1, and then plug that value into the C3s and all the equations here, and we get a vector solution such as C1 will have to be 1, C2 will have to be -1, and C3 will have to be 1. Now the system that we just solved was the following. C1 times the first vector plus C2 times the second vector plus C3 times the third vector is equal to the 0 vector. And we just discovered that this has a non-trivial solution where C1 is 1, C2 is -1, C3 is 1. So plugging these in, we get the following, that u minus v plus x has to be equal to the 0 vector. And once we have this equation, we can solve it for each of the 3 vectors involved separately. So we get 3 different possible ways to express this relationship. We could say that vector u is equal to vector v minus vector x, we can say that vector v is equal to vector u plus vector x, or we could say that vector x is equal to negative vector u plus vector v. And since we can construct any vector by doing a linear combination of the other two vectors, that means that these three vectors are linearly dependent. I'll leave it to you to verify any of these relationships right here for these three vectors. Okay, let's go to the next page. A basis of a vector space V, which is a subset of Rn, is a linearly independent set of vectors B such that span of B will equal that vector space. So basically, B will be a minimum set of vectors such that the span of those vectors will produce the entire space in question. Find a basis for the vector space in R2 defined by the linear equation 3x minus 5y is equal to 0. So y must therefore be equal to 3/5 of x. This would be a line through the origin with a slope of 3/5. So right 5 up 3, looking something like this. Now, as we discussed before, in R2, lines through the origin do form vector spaces because they are closed under vector addition and closed under scalar multiplication. We need to find a set of vectors such that the span of that set will equal this vector space. Well, because this vector space is linear, we really just need one vector on it. And we can go ahead and pick that vector 5, 3. This is a vector on this line. And if we do all scalar multiples of this vector, we will just produce the entire line. Therefore, we know that the span of this one vector, 5, 3, will equal this vector space. Let's call this vector space V sub 1. Now, we need at least one vector in order to do a span. And since this one vector was sufficient to create the entire vector space by spanning it, then we can call this one vector a basis. So capital B will be this set of vectors, in this case only one vector, 5, 3. So let's read the statement again. A basis of a vector space V is a linearly independent set of vectors B such that the span of B is V. In this case, the basis B has only one vector in it, and a set with one vector, as long as it's not the zero vector, is always going to be a linearly independent set. And so this will be a sufficient basis. Now, this isn't the only vector I could have picked. I could have picked any vector on this orange line and then done the span of that vector to produce the entire orange line. The only vector I cannot pick to form the basis is the zero vector, because the span of the zero vector is just the zero vector still. It won't produce the entire orange line. So I could have said the basis B was equal to the set of just one vector, where that one vector was -5, -3, or 10, 6, or 15, 9. Basically, any scalar multiple of the vector I have written currently, except for the 0 times that vector, would be an acceptable vector to use as my basis. For the next one, find a basis for the xz plane in R3. So I'll draw a little representation of what this plane looks like. It's the plane that contains the x and z axes. It'd be this plane right here. Now, we're only seeing a portion of it in this particular viewing, but to find a basis for this plane, we need to find the minimum number of vectors such that the span of those vectors will equal this plane. So our basis will be a set of vectors. They have to be three-dimensional vectors. Let's pick the following vectors. Let's do the standard basis vector I that points one unit in the x direction. And that vector, if you recall, was 1, 0, 0. Now, as my second vector, I don't want to pick a multiple of I. For example, I don't want to pick anything that's also on the x-axis, like this green vector, because the span of the green and red, since they're collinear, will only produce the x-axis. It won't produce a plane. So I have to make sure to pick a vector that terminates off of the x-axis. I could pick this vector that's in the xz plane, or what's commonly done is just to pick another standard basis vector, but the one pointing up. This was the k standard basis vector. It points one unit in the z direction, and its components are 0, 0, 1. And these are the only two vectors I need in order to span the xz plane. All linear combinations of these two vectors will produce all the vectors that are in the xz plane. These two vectors are linearly independent. Neither one is a multiple of the other. And furthermore, we have that the span of this set of vectors does equal the xy plane, which is our second vector space in question here. I had to pick any two vectors in the xz plane that were linearly independent of each other, so not collinear. And those two vectors would have been a sufficient basis for the vector space that is the xy plane. But what is certainly true is that I needed two vectors. One vector alone, when you span it, can't produce a plane. It would produce a line. So we needed two vectors and no more than two vectors to form a basis. If I do try to put a third vector in here that's also in the xz plane, that third vector, for example, imagine a blue vector like this that's also in the xz plane, that third vector is a linear combination of the green and the red. So if I put that third vector in here, call it vector w for now, then the three vectors in my basis would not be linearly independent because w is a linear combination of the other two. So you'd want to remove it and go back down to just two vectors only to form a basis. All the vectors in the basis have to be linearly independent. So in this case, we need two and only two vectors. Now find a basis for the vector space in R3 defined by the linear equation 4x minus y plus 3z is equal to 0. Let's go ahead and graph this using GeoGebra 3D to get a sense for what this equation produces. So I typed in the equation into GeoGebra, and it produces this plane, and you can see that the plane does in fact pass through the origin. So this is a vector space, and we want to find a basis for this vector space. Now this vector space is a plane, and so we will need more than one vector to span it. We need two vectors that are in this plane and that are not collinear. If I can find two such vectors that are in this plane and not collinear, then those two vectors will be independent of each other, and they're both in the plane, so the span of the two vectors would wind up producing the entire plane. So this boils down to find two vectors that terminate on this plane that are not multiples of each other. Well, we could do this a number of ways. To find a point that's on this plane, simply pick x and y to be any two numbers and solve for z. Or pick x and z to be two numbers and then solve for y. Basically, just find an ordered triplet that satisfies the equation by plugging in two of the three and solving for the third. So making a table of points, I discover that if x is 3 and y is 0, plug these values in and solve for z, you will get that z has to be negative 4. And I picked x and y to be values so that my z coordinate would not be a fraction. But it's okay if you find one where z is a fraction. I also discovered that if I plug in 0 for x and 3 for y, that my z coordinate will need to be 1. So these points, x, y, and z, both of these points, satisfy this equation. So therefore, they're both on the plane. Also notice that they are not multiples of each other. So my first vector is going to be 3, 0, negative 4. And my second vector is going to be 0, 3, 1. And these are not multiples of each other. Therefore, they are not collinear. And their span will be the plane. And their span will be the plane that is our third vector space here. So this will form our basis. Put the vector u and vector v as we just defined them as our basis, and the span of this basis will produce this plane, which is our third vector space. If I pick a third vector and try to put it in the basis, then that third vector will also be coplanar with the other two. Therefore, it would be possible to express the third vector as a linear combination of the other two. Therefore, we don't want to put a third vector in here because if we do, then I'll have a set of three vectors that are now linearly dependent. And a basis can only contain vectors that are linearly independent. This is why I say that a basis, in effect, is the smallest possible set of vectors whose span will be the entire vector space. It does not allow for any extraneous vectors to be included in the set. However, you do have the freedom to pick a different collection of vectors, as long as it's the same number of vectors to form the basis. Okay, this last sentence here at the bottom of the page says that the dimension of a vector space V is the number of vectors in any basis of the space. It is denoted dim, or dimension, of V. Identify the dimension of each vector space above. Note that a vector space can have more than one basis, but it cannot have more than one dimension. So just working backwards, for our third vector space, we found two vectors that form a basis. So we say that the dimension of this third vector space is going to be 2. Every single basis for this vector space will need to have two linearly independent vectors in it, but there are multiple choices of the two vectors. In our second example, the dimension of this vector space will also be 2, because its basis also has 2 vectors in it. And in our first example, the dimension of this vector space is going to be 1, because we only needed 1 vector in its basis. Okay, let's go to the next page. For any vector space V that's equal to the span of some set S in Rn, a basis B can be found among the vectors in S. In other words, there exists a basis B such that B is a subset of S, and that the span of B is the same thing as the span of S. So along this idea that a basis B is a minimum set that spans the vector space, sometimes a set S might have some extraneous vectors in there, and we can remove some of them without changing the span, and we want to continue to do so until the only vectors that are left remaining in the set are linearly independent, at which point we can call that collection a basis. Find such a basis for the vector space below and identify the dimension of the vector space. Okay, so this vector space is a span of 1, 2, 3, 4, 5 different vectors, all in R3. Okay, now it's possible that all 5 of these vectors are collinear, right? One of the vectors could be this line, and then another could just be an extension of it, and then maybe an extension of that, and then maybe in the same direction but opposite. And so if these were the 5 vectors and they're all collinear, then the span of the 5 vectors is equal to a line in 3 space, which means I would only really need one of the 5 vectors in order to form a basis, and it would be able to be any of these 5. But maybe all 5 vectors are not collinear, but maybe they're all coplanar. So imagine a plane, and all 5 vectors lie in that plane, in which case we would only really need 2 of them, so we would only need 2 of them to span the entire space. But maybe they are not coplanar nor collinear. Perhaps they point in different directions like the x, y, and z axes do, in which case the span would be all of R3, and we would need 3 vectors in that basis instead of the 5 that we have. So we need to determine what the case is here, what kind of vector space this actually is. Is it a line through the origin, a plane through the origin, or is it all of R3? And depending on which case it is, that will determine in the end ultimately how many vectors we need in its basis. All right, the statement above suggests that we have a span of a set S, and this S has 5 vectors in it. From this set S, we're going to remove a minimum of 2 vectors to reduce down to a basis. We can construct a basis for this vector space by using a subset of vectors from this set S. We just need to remove all the ones that are extraneous, which are linear combinations of the others. Okay, let's label the vectors in this set the following way: vector x, vector y, vector z, vector u, and vector v. Let's look at the first 2. Notice that if we double vector x, we will produce vector y. This tells me that we don't need to include both of these vectors. They are linearly dependent on each other. One is just a scalar multiple of the other, therefore x and y are collinear. The span of one will produce the span of the other. So we can remove one of them safely, and let's just remove the y. But you also can choose to remove the x. We'll remove y from the set S. So I'll put an x through it. Now let's compare vector x to vector z. Notice that they are not multiples of each other in either direction. You cannot scale z to make x, and you cannot scale x to make z. So this means that x and z are independent. So we can keep them both in the set so far. Now let's move on to vector u. The question is, does vector u coplanar with vectors x and z, or is it also independent of the 2? Now to determine that, if I look at vectors x, z, and u as a set and ask if they are independent of each other or not, that will form a 3 by 3 matrix that's square. So if I calculate the determinant of the matrix by putting as its columns vectors x, z, and u, right, this would be the following matrix. And when we calculate this determinant, we do get 0. And when that happens, this suggests that the vectors are linearly dependent. Therefore, we know that adding the vector u to the collection of x and z created a dependent set, which means that u was coplanar with x and z, which means that we don't want to include this latest vector u. We can eliminate it. Now, I could have chosen to remove x or z instead, but then I would have to make sure that u is still independent, that the set of u with the one that remains is still an independent set. Since I've already verified that x and z are independent, but then adding u to the mix caused the set to become dependent, then I just want to take u back out of it. Now let's consider whether the vector v is also coplanar with x and z. And since x, z, and v will form a 3 by 3 matrix, I can again use determinant to help determine whether that set is linearly independent or dependent. So putting these three vectors into a matrix, we get the following. And when you calculate this determinant, you get a non-zero number, which suggests that these three vectors are independent. As such, I can construct a basis for this same vector space by keeping only the vectors x, z, and v. And that will form a basis for the vector space capital V. Furthermore, if I were to do the span of these three vectors in our basis, we would get vector v, and we know that all three are linearly independent. So that's why we can call B a basis. And the dimension of this vector space, therefore, has to be 3, which tells me that the vector space itself is R3. Not a plane through the origin, not a line through the origin, not the origin only, but it's the entire space R3. Now let's use technology and look at these 5 vectors. Okay, I've plotted the 5 vectors. You may have to zoom out a little bit to see where the last vector ends. But let me zoom back in now. All right, the first 2 vectors in our set were the green and the red, and notice they were collinear, so we didn't need to keep both in our basis, and we chose to get rid of the y vector. Next, we determined that the x and z were linearly independent, that they were not multiples of each other. You can see that clearly from the imagery. And then we looked at vector u in black, and it did turn out that vector u is coplanar with vectors z and x. So they lie in the same plane, and you can see that easily from this angle here. The black, the blue, and the red are coplanar. So we didn't need to keep all 3 of these. Now from the visual, I can have eliminated, it's easy to see I could have eliminated any one of them. Could have eliminated the black, because the blue and red are still linearly independent and they'll span that same plane. Or I could have removed the blue and kept the black and red, they will still span the same plane that all 3 are in. Or I could have removed the red and kept the black and blue, because that will still span the same plane that all 3 of these vectors are in. But we don't need all 3. So I chose to get rid of vector u. And then we discover now that vector v is not linearly dependent with vectors z and x, because vector v is not in the same plane. Right? You cannot express vector v as a linear combination of the blue and the red. Nor can we express the red in terms of the blue and purple. Nor can we express the blue as a combination of the purple and red. So these 3 vectors ultimately form a linearly independent set. And their span, because we point all directions, will be all of R3. Any point in R3 can be obtained from these 3 vectors through some appropriate linear combination of them. And the dimension of this vector space is 3. Okay, now the last page. A subspace is a subset of a vector space that is also a vector space. Summarize all types of subspaces of both R2 and R3. For each type, give a sample basis and identify the dimension of the subspace. When we say subset, we're talking about this notation here. A is a subset of B, and this allows for possible equality, this symbol right there. So if A and B are the same set, then we can still say that A is a subset of B. So let's make sure that that's clear. So focusing on the subspaces of R2, all the different kinds of vector spaces that are subsets of R2. The trivial one is the 0 vector. So this is the subspace that is only the 0 vector, no other vector in it. This is a case, though, where we say there is no basis, because a basis has to be a linearly independent set, and the 0 vector cannot be in a set that is linearly independent. So there simply is no basis, and we say its dimension is 0. It's a trivial, non-interesting subspace, but it's still a subspace. Now, the other kind of vector space that's a subset of R2 is the subspace that is the lines through the origin. For example, any multiple of the vector 1, 2. This will produce a line through the origin, and any vector on that line will serve as a basis. So the vector 1, 2 itself will work as a basis vector, or you could pick the vector, any multiple of this. So the vector 2, 4, the vector 3, 6, the vector -1, -2. Let any one vector on this line, that's not the zero vector, be the vector that's in the basis. And the dimension will be 1. And the other possible subspace of R2 is actually all of R2. And a basis of this example, and a basis of all of R2, you just have to pick any two vectors in R2 that are not collinear. So they have to be linearly independent. The obvious choices are the standard basis vectors, I and j. We've talked about that before. The span of these two vectors will produce all of R2, and these two vectors are linearly independent. Of course, this is not the only choice of two vectors for a basis, but whatever basis you pick, you can only pick two that have to be linearly independent, and that will span all of R2, and the dimension of this vector space is 2. Now let's look at the subspaces of R3. The 0 vector, our trivial subspace, has 3 zeros. There is no basis for this, and we say the dimension is 0. The other kind of subspace, that's a subset of R3, are lines through the origin. So, for example, any multiple of 1, 2, 3 will produce a line through the origin. Therefore, that vector itself could be the vector you use for the basis. Or you can do any multiple. So you could do 2, 4, 6, 3, 6, 9, -1, -2, -3, etc., as long as you pick a non-zero vector that's in the space, and it will serve as its basis, and the dimension is just 1. Now, planes through the origin, if you recall, had two direction vectors. So we could do t times 1, 2, 3, and then plus s times, and then the second vector I pick has to be independent of the first vector. We don't want them to be collinear, otherwise their span will just be a line again. So let's pick 1, 2, -3. So these two vectors are not multiples of each other, so they are independent, and they alone will serve as a basis. Of course, you can pick any two vectors that are on this plane, as long as those two vectors are not multiples of each other, and use those two vectors as the basis. And the dimension here will be 2, because we have two vectors in the basis. And then finally, the other kind of subspace of R3 will be all of R3. And I'm going to pick as its basis the three standard basis vectors, 1, 0, 0, 0, 1, 0, and 0, 0, 1. But you can pick any three vectors you want as long as they form a linearly independent set, so that their span will be all of R3, and we have a three-dimensional vector space. And this wraps up our second half of our discussion on vector spaces in Rn.